Okay, so Newton's law of gravitation, he did this as a related rate to each other, but eventually they were able, it was Cavendish and Von Jolly, I believe, they were able to calculate this G value, although Newton was the first one to really come up with this. And we can calculate the forces that attract two objects, even small ones. You could calculate the attraction of two objects to each other. But generally speaking, we talk about the mass of one planet, or maybe a satellite, or the mass of one planet and its moon, which I guess is a satellite, or two planets to each other, or something like that. But this could work for any of them. Now, when you do calculate the force, and remember, I think we talked about this before, that if you took this right here, this G value, which by the way, I'll write it in another slide too, but Cavendish and Von Jolly came up with 6.673 times 10 to the negative 11 Newton meters squared over kilogram squared. And they were able to do that as a very quick side note here. They took two very heavy lead balls and they measured how much they attracted to each other, and were actually able to calculate that. And then once they had that attraction, which would be this force right here, they had the mass of one ball, the mass of the other, and the distance between the centers of both of them, and kind of make a note of this one too. This R value is from the center, and they were able to square that. They were able to come up with G. So when you calculate this here on the surface of Earth, that turns out to be that 9.8 meters per second squared that we always talk about, and then we multiply it by the mass, and that comes up with our F sub G. Making sure too that you take the distance between two of them. So if you had a moon or something like that, and you were trying to calculate that, would, wow, the distance, that would be your R. Okay. All right. So let's go ahead and put this into motion here. The gravitational force is keeping satellites in motion. And so when we go to calculate this, we find, using Newton's law of gravitation, we have the mass of the satellite, mass of the planet, usually it's Earth that we're putting satellites around, but I guess you never know, mass of satellite times v squared over r. So this is your centripetal force requirement. This is your gravitational pull requirement. So far, we've looked at centripetal forces that are normal forces, that are tension forces, that are friction forces, and this is one where it's the gravitational force keeping the object in motion. So that cancels, and we come up with a velocity of an orbiting satellite that is this distance from the center of the Earth. Okay. So when we calculate this, I think the next one is the Hubble telescope. I hope that is. Yep. And so when we calculate this, we have to realize that what we're taking is the velocity is going to equal G times the mass of the planet over R. But also realize that this is going to be 6.38 times 10 to the 6th. Plus, and if that's going to be in meters, then that should be 598,000 meters, okay? Because that's in meters. So meters. So we're not exactly going to the center of the telescope, but it's so small compared to Earth that I think that'll be fine. G is that constant, 6.673 times 10 to the negative 11, and the mass of planet Earth is right there. Thanks to Cavendish and Von Jolly, we have that. And so when you calculate that, it turns out to be like 7.56 times 10 to the 3 meters per second. Okay. And we could talk a little bit about launching of satellites, but if you were to launch a satellite at a certain height, the curvature of the Earth, every 8,000 meters you travel, I did not do this to scale, the Earth will drop down 5 meters. And so if you're able to launch from a certain height at 8,000 meters per second, you're able to put a satellite in orbit, and it's a circular orbit. If you go greater than 8,000 meters per second, you are able to put a satellite in elliptical orbit. So if you want to know more about that, you take astronomy from Mr. Crittenkamp. All right, if you go too fast, though, what's going to happen is you are going to have the object, the rocket, the satellite, whatnot, escape from the gravitational pull. And I won't go into deriving that, but the escape speed is going to be the square root of 2 times this constant g times the mass of the planet times the radius of the planet. And you could calculate Earth's escape speed by just plugging in those numbers, and I don't think I'm going to go into all of that, but g, of course, being 6.673 times 10 to the negative 11, mass of Earth being like roughly 6 times 10 to the 24th, and the radius of Earth being 6.4 times 10 to the 6th. And when you do that, you're going to get an escape speed of 1.12 times 10 to the 4th meter per second. So if you go that fast, you will escape the gravity pull. Okay, one other real quick thing that I want to talk about, and it might be a quick question on the test, is that a black hole is really interesting. The speed of light is 3 times 10 to the 8th meters per second. That's sort of the speed limit of the universe. Nothing has been shown or proven to go faster than that. And so a black hole is very interesting because if you think about the escape speed of something that has infinite mass, which is just, if you think about astronomy and astrophysics too long, your brain will explode. But if you think about an infinite mass, what's happening here is that the mass, or I should say infinite density, I hope that's what I said. What happens is the mass of the planet's going up and the radius going down because density is mass over volume, right? So if your density is infinite, that means you have an infinitely high mass over an infinitely small radius. And when that happens, what happens to your escape speed here? Well, it also becomes infinite, and it way escapes or way exceeds 3 times 10 to the 8th. So not even light can escape a black hole.